Every time you drop your keys, they fall to the floor.
Right.
Like every time you flip a switch, a light bulb turns on. For you, going about your daily life, the universe seems pretty reliable.
Yeah, it really does.
We have mathematical formulas that perfectly explain why those keys fall, and we have entirely different formulas that, perfectly explain how the electrons flow through that light bulb. It gives us this comforting illusion that modern science basically has reality figured out.
Right. I mean, we send rovers to Mars, we carry supercomputers in our pockets.
Exactly. But what if I told you that right now, in the centers of black holes, the math that explains your falling keys and the math that explains your light bulb are literally at war with each other,
Yeah.
and the universe is throwing a fatal error?
Well, it is a massive structural breakdown.
Hmm.
And we aren't just talking about a minor rounding error or, a polite disagreement among academics. We're talking about the two foundational pillars of physics, fundamentally refusing to coexist.
Welcome to the deep dive. Today, we are looking at a truly mind-bending excerpt. It's titled The Quantum Gravity Crisis and the Breakdown of Mathematics, and it's drawn from a much larger, incredibly dense work called The Mathematical Architecture of a Unified Universe.
It is a dense read, for sure.
Oh, absolutely. But our mission today is to explore this profound, unresolved crisis that is literally keeping theoretical physicists awake at night. We want to show you why the ultimate blueprint of reality is currently speaking a language we simply don't have the vocabulary to translate. Okay, let's unpack this. Where exactly does this foundational conflict begin?
Well, the conflict begins with the fact that we don't just have one rule book for the universe. We have two.
Yeah.
And, I mean, they're both spectacularly successful in their own realms.
Right.
On one side, we have Albert Einstein's general relativity. This is basically our operating system for the macrocosmos. It describes the massive, heavy things in the universe.
Like planets and stars.
Exactly. It predicts the orbits of planets, it explains how galaxies cluster together, and it maps out how the physical fabric of space-time itself curves and bends.
And then on the flip side, we have quantum mechanics, the rulebook for the exceedingly tiny.
Right. Quantum mechanics is the framework for the microcosmos. It describes the chaotic behavior of subatomic particles, quarks, electrons, photons. And we really need to emphasize that individually, both of these mathematical frameworks are tested to absolute near perfection.
Yeah, like the smartphone you were likely listening to this on relies on quantum mechanics to manage the transistors in its microchip, right?
100%. And it relies on general relativity to sync its GPS with satellites orbiting the Earth.
So they both work. They govern our modern world. But the source text calls this the clash between geometric smoothness and quantum chaos. Why are these two highly successful systems at war with each other?
It's because the underlying mathematical languages they are written in are built on completely contradictory assumptions about how reality functions. General relativity relies on continuous, non-Euclidean differential geometry.
Okay, wait, let's break that down for the listener because that is a mouthful. Differential geometry, non-Euclidean. What are we actually picturing there?
Think about the geometry you learn in high school Euclidean geometry. It assumes space is flat, like a piece of grid paper. Lines are straight, angles add up neatly.
Right, a triangle is a triangle.
Exactly. But differential geometry is the mathematics of curved surfaces. Imagine trying to draw a straight line on the surface of a sphere, or like a saddle. Einstein used this specific branch of math because his theory assumes that space-time is a physical deterministic fabric that smoothly warps and curves in response to mass.
Like the classic analogy of the heavy bowling ball sitting on a perfectly smooth trampoline.
Yes, perfect analogy. The trampoline stretches continuously, there are no tears, no sudden jumps, no gaps. The math flows like a perfectly smooth, uninterrupted river.
Okay, so general relativity is smooth, predictable, continuous. But quantum mechanics is, none of those things.
Not even close. Quantum mechanics is built on discrete, probabilistic linear algebra.
That sounds intense.
It doesn't deal with smooth curves. It deals with arrays of numbers, probability matrices, and sudden discrete leaps. In the quantum world, energy isn't a smooth river. It is chunky. It's delivered in specific, indivisible packets called quanta.
And the text points out that this clash becomes violently obvious when we get down to something called the Planck scale, which, if I remember correctly, is a measurement so unfathomably small that it's basically the pixel size of the universe.
It really is. It's the absolute minimum limit where our conventional understanding of space and time even makes sense. When you zoom in that incredibly close, quantum mechanics tells us that reality is governed by the Heisenberg uncertainty principle.
Right, where everything is based on chance and probabilities.
Exactly. At that microscopic level, space-time completely stops behaving like Einstein's smooth trampoline. It dissolves into a phenomenon physicists call quantum foam.
I was trying to visualize quantum foam earlier. At first, it sounds pleasant, like a latte or something, but the reality is a lot more aggressive.
Oh yeah, it is not pleasant.
It's a chaotic, violent sea where virtual particles are literally popping into existence and annihilating each other fractions of a millisecond later. It actually made me think of this analogy for you listening. Imagine general relativity is a beautiful, classical landscape painting hanging in a museum. From across the room, the sky is perfectly smooth, the colors blend seamlessly, it's continuous and predictable.
I like this.
But then you walk across the room and press your nose directly against the canvas to look at the tiniest details. That's quantum mechanics. And suddenly you realize it's not smooth paint at all. It's actually composed of millions of frantic, chaotic, vibrating dots that absolutely refuse to sit still.
That paints a vivid picture of the sheer structural mismatch. You cannot use the mathematics of a smooth, blended brushstroke to calculate the trajectory of a billion frantic, vibrating dots.
But I have to push back here. You and I and the listener, we all live in the exact same universe. A planet is made of atoms. So if reality is fundamentally just one singular universe,
Right.
how can it operate on two completely incompatible operating systems depending entirely on how closely you zoom in?
What's fascinating here is that the universe itself isn't operating on two broken systems. The universe knows exactly what it's doing. The problem is our translation of it.
Oh, translation.
Yes. When you attempt to apply the smooth geometric calculus of relativity to this hyper-probabilistic quantum environment, it creates immediate fatal mathematical contradictions. It's like trying to use the rules of fluid dynamics, the math that predicts ocean currents, to track the random bouncing path of a single isolated water molecule.
It just doesn't work.
The formulas just spit out nonsense. It exposes a severe gaping hole in our scientific language.
Which is a perfect segue into where this chalkboard problem becomes a physical nightmare. It's one thing to say, hey, these two math equations don't look good next to each other on paper. But the source text makes it very clear that there are actual physical locations in our universe where scientists are forced to use both rule books at the exact same time.
Yes. The universe provides two specific cosmological crucibles, where physicists have absolutely no choice but to merge these equations: the core singularity of a black hole and the initial microscopic state of the Big Bang.
Wait, I'm lost. If a black hole is basically the heaviest, most massive object in the universe, shouldn't the math just get infinitely huge? Why do we even need the microscopic math of quantum mechanics for something that big? And where does a mathematical zero come from in all of this?
Well, that is the crux of the issue. You have an immense astronomical amount of mass, like entire dead stars worth of mass.
Okay.
Because of that extreme mass, you absolutely need general relativity to calculate the crushing gravity. But that mass has collapsed in on itself. It has been crushed down into a microscopic arena, far smaller than an atom.
Oh, wow.
Yeah, because the physical space is subatomic, you absolutely need quantum mechanics. You are forcing the ultimate macro force into the ultimate micro arena. And this triggers the exact mechanical failure tearing physics apart, the division by zero crisis.
Okay, walk us through the actual mechanics of that. Why are we dividing by zero?
It comes down to calculating density. The formula for density is mass divided by volume. In a black hole or the moment of the Big Bang, you take an enormous mass and you divide it by a physical volume that is rapidly shrinking. Let's do the math here. If you divide a mass of 10 by a volume of 1, the density is 10.
Right.
If you divide 10 by a smaller volume, say 0.1, the density jumps to 100. Divide 10 by 0.001, it jumps to 10,000.
So the smaller the volume gets, the massively higher the density goes.
Precisely. And in a singularity, the math suggests the volume collapses entirely until it reaches absolute zero. So you end up dividing an enormous mass by zero. And in pure mathematics, dividing by zero causes the equation to spiral out of control, resulting in an undefined absolute infinity.
Here's where it gets really interesting, especially for you listening at home, because this touches on something profound about the physical world. In pure math on a piece of paper, an undefined infinity is just a quirk of the numbers. But physical reality cannot contain actual infinity.
No, it cannot.
You can't have an object with infinite density occupying a strictly finite amount of space in our universe. It violates the basic conservation of energy and logic. So when scientists run these equations and get infinity as an answer, it doesn't mean the black hole is actually infinitely dense. It means our scientific tools have hit a brick wall.
It is essentially a blue screen of death for theoretical physics.
Yeah.
The math is telling us, I don't have the capacity to process what you were asking.
I have to ask this because I think everyone listening has encountered this. Every time I watch a sci-fi movie or even a highly produced pop science documentary, the narrator always uses this booming, dramatic voice to talk about the infinite density of a black hole. Are they all basically lying to us? Are they just describing a giant math error in our current physics and dressing it up as a cosmic fact?
If we connect this to the bigger picture, yes, they absolutely are.
That's wild.
When astrophysicists talk about the infinite density of a singularity, they aren't describing a verified physical object that they've somehow measured. They're describing the exact boundary line where human understanding drops off a cliff. The appearance of infinity in those equations is proof that we lack the scientific vocabulary to interpret these cosmic extremes.
So our ultimate cosmic mystery is, at its core, a syntax error, which leaves us with a massive problem to solve. If the entire foundation of modern physics breaks down specifically because the math reaches a zero volume and divides by zero, how do we fix it?
Well, the current strategy among modern theoretical physicists is to radically rewrite the fundamental rules of the universe. They are trying to engineer completely new mathematical vocabularies designed specifically to ensure the universe can never ever reach a volume of zero.
The source text highlights two massive competing workarounds for this. Let's start with the one that tries to change the stuff inside the universe. String theory.
String theory is a radical reframing of the ingredients of reality. Traditionally, the standard model of physics has treated the fundamental building blocks of matter like an electron or a quark as zero-dimensional point particles.
Meaning they are just mathematical points. They have mass, but they take up literally zero physical space.
Right. And as we just discussed, if a particle has zero volume and you crush a bunch of them together in a black hole, you inevitably divide by zero. So string theory replaces those zero-dimensional points with one-dimensional vibrating strings of energy.
And here's the part that always trips me up. To make the math for these vibrating strings actually work, string theory requires the universe to have 11 dimensions. We experience 3 dimensions of space and 1 of time. Where are the other 7 coming from, and why do we even need them? It sounds like we're just making things up to cheat the system.
It does sound like a cheat code, I admit. But it's a mathematical necessity born of probability. Remember how we said quantum mechanics is based on probabilities?
Yeah.
In a stable universe, the sum of all probabilities for an event must equal exactly 100%. But when physicists tried to calculate the vibrations of these strings using just our normal 3 dimensions of space, the math started spitting out nonsensical answers, like negative probabilities or probabilities of 120%, which is physically impossible.
So the math was breaking again.
Exactly. The strings didn't have enough mathematical room to vibrate properly. But physicists discovered that if you add extra spatial dimensions to the equations, giving the strings more directions to move in, those mathematical anomalies cancel each other out.
Fascinating.
The extra dimensions act like mathematical shock absorbers, dispersing the energy until the probabilities settle back perfectly at 100%. The equations demand 11 dimensions just to balance.
That is wild. But getting back to our black hole problem, how does replacing a point with an 11-dimensional string actually solve the division by zero crisis?
It removes the zero. By assigning a fundamental physical length to these strings, you ensure that the most basic building block of reality is not a dimensionless point. It has size. And if it has size, it can never be crushed down into an absolute zero volume. The denominator in our density equation can get incredibly small, but it can never be zero. The math survives.
It's an elegant hack. You just redefine the fundamental unit of matter so the error can't happen. Okay, so string theory fixes this by changing the stuff inside the universe. But what if the stuff isn't the problem? What if the universe itself is the problem? The source text outlines a competing theory for that too.
Yes, that is the exact premise of the second major workaround, loop quantum gravity, or LQG. Instead of changing the particles that exist within space, loop quantum gravity seeks to change the fundamental nature of space itself.
Going back to Einstein's smooth trampoline, we're tearing up the trampoline.
Precisely. General relativity assumes space is a continuous, infinitely divisible background. Loop quantum gravity throws that out. It suggests that space itself is quantized. It proposes that the fabric of the universe is woven out of tiny, discrete, finite loops. Space is essentially made of pixels.
I love this concept because it immediately makes sense if you think about digital media. Think about a digital photograph on your computer screen. From a distance, the image looks completely smooth and continuous. But if you zoom in on it enough, eventually you see the individual blocky pixels.
Exactly.
You can't zoom in halfway between the pixels. You can't have a quarter of a pixel. That fundamental square is the absolute limit of the image's geometry.
And that maps beautifully to what LQG proposes about the geometry of the universe. In this theory, volume isn't an empty container. It is a discrete network of relations.
So if I'm picturing this right in a physical sense, is it kind of like a massive Lego structure? Imagine you build a gigantic hollow cube out of Legos. You can put immense pressure on it. You can crush that Lego structure down. You can pack all the pieces tightly together in the center. But no matter how hard a black hole crushes it, you can never crush that structure to be smaller than a single individual Lego brick. The brick itself occupies finite volume.
And mathematically, that saves physics. Because the fabric of space itself cannot be compressed beyond the boundary of a single pixel or Lego brick, the volume inside a black hole can never reach absolute zero. The geometric limit prevents the division by zero error, avoiding the singularity crisis entirely. Both string theory and loop quantum gravity are ultimately ingenious attempts to prevent the math from crashing.
Okay, let's take a deep breath and step back for a second. We've covered a lot of ground today. We've got quantum foam, 11-dimensional mathematical shock absorbers, and literal pixels of physical space. So what does this all mean? For you listening right now during your commute or while making dinner, why should you care about this highly theoretical, incredibly abstract debate?
You should care because the persistent, decades-long struggle to reconcile these theories reveals a shocking, overarching truth about the limits of human achievement. We are increasingly realizing that the scientific community is likely facing a crisis of mathematics rather than a crisis of physics.
A crisis of math, meaning the problem isn't the universe.
The universe is doing what it has always done, and our observational data is better than ever. We have telescopes taking pictures of black holes. We have colliders smashing atoms. The problem is that the calculus and the geometric tools developed over the past few centuries simply lack the vocabulary to express a unified theory of everything. Our language has run out of words. The tools aren't sophisticated enough to describe the reality we're looking at.
And as the source text notes, this actually has a profound historical precedent. We've hit this exact wall before, haven't we?
Multiple times. Think back to Isaac Newton in the late 17th century. When Newton was trying to unlock the secrets of classical mechanics, trying to figure out how planets moved in curves while gravity pulled them in straight lines, the standard algebra and geometry of his day weren't good enough.
Right.
The math couldn't handle continuous changing rates of motion. So what did he do? He literally had to invent a completely new branch of mathematics, calculus, just to be able to write down his physical theories.
He couldn't write the poem until he invented the alphabet.
Exactly. And the same thing happened with Einstein. When Einstein had his revolutionary idea that massive objects warp space-time, standard high school Euclidean geometry couldn't compute it. He had to scour the mathematical world until he found Riemannian geometry, a highly complex, obscure mathematics of curved spaces, to make the theory of general relativity function.
So modern physics is basically stuck in the waiting room. We have all this incredible data, we have the ambition, but we are sitting around waiting for the next great mathematical revolution to build a bridge between Einstein's smooth, heavy cosmos and the chaotic, pixelated quantum world.
This raises an important question about the nature of progress. Human knowledge always hits these distinct ceilings. We reach a point where our current cognitive tools fail us, and we plateau until someone invents a new, unprecedented language to push us through the ceiling. The mathematical tools of the past 3 centuries have taken us to the very edge of the black hole, but they cannot take us inside.
It really shifts your perspective. We started this deep dive talking about how confident we feel in modern science, feeling like we hold the master blueprint. But really, we are holding half a blueprint written in English and half a blueprint written in ancient Sumerian, and we are just aggressively trying to tape them together.
And we are getting division by zero errors for our trouble.
Right. So I want to leave you, the listener, with one final thought to mull over today. Think about Isaac Newton having to invent the entire field of calculus just to understand why an apple falls. Think about Einstein having to adopt non-Euclidean geometry just to map out the curves of space-time. If these massive paradigm-shifting leaps in human understanding required entirely new, incredibly complex mathematical languages, what if the mathematical language needed to finally note the universe as something the human brain isn't even biologically wired to comprehend yet? Are we just waiting for the next Newton to be born and invent the next calculus? Or is the universe written in a code that we are fundamentally biologically locked out of reading?